Hi, in this video, we will be discussing the 0-1 knapsack problem. First, we will start with the problem statement. Then, we will dive into the examples. Then, we will discuss how to solve this problem using the brute force method, that is using the recursion method. Then, we will discuss how the greedy algorithm fails to solve the 0-1 knapsack problem. And finally, we will be discussing the optimization of the recursion using the dynamic programming, using the memorization table method and the tabulation method. And in the end, we will discuss the further space optimization for the 0-1 knapsack problem. So the problem statement is as follows. You are given weights and values of n items. You need to put these items in a knapsack of capacity W to get the maximum total value in the knapsack. Note that we have only one quantity of each item. So basically what this problem says that we are having n items and those items are having values and weights. So we are supposed to have two arrays. One will denote the value of the item and the other will denote the weight of the item. These will start with 0 indexing and will be ending at the n-1th index because we are having n items. So this will be the array which we will be getting, and we are also having a knapsack. Let's say this is our knapsack of capacity W. Now we need to pick the elements from the given items such that we need to maximize the we need to find the maximum value we can get such that the knapsack does not overflows. Let us consider an example when we are given three items of the following values, with having the following values and the following weights. Let's name these items A, B and C, and let's say the knapsack capacity is W equals to 12. Now let us try to implement the brute force approach, that is using recursion, to solve this problem. In brute force approach, we just generate all the permutations that are possible and find the value which is possible in that permutation and see if that we can pick that permutation by checking if the weight of that permutation is less than the knapsack capacity, and if that is feasible then we pick that permutation, and or I can say that we can pick the maximum value among all the permutations formed. So what are we exactly doing? Let's say initially we are having knapsack empty, that is we are having the items picked 0 and hence the value is also 0. Now I will just see, I will have two choices for every element, either to pick an element or to not pick an element. Okay, so I will just see for element C, I have two choices, either I will pick it or I will not pick it. After making any of the following choices for this element, that is item C, I will move on to the next item and I will make the choice for item B. Here also I have two choices, either to pick this or to leave this. Then I will move on to the next item, which is item A. Here also I have two choices, either to pick this or to not pick this. Finally, after making all of these choices, I will have all the permutations that are possible will be formed, and I will pick the permutation giving me the maximum value and its weight should be less than equal to my knapsack capacity. That will be my brute force idea or brute force approach. Let's see how this works by drawing the recursive tree. So initially I'm having value 0, weight is also 0. Now from here I have two choices. I can pick element C or I will not pick C, right? So if I just pick C, then again I will have two choices, either to pick D or not to pick D. If I choose to pick B, then I have again two choices, either to pick A or to leave A, right? Now here, if I chose not to pick B, again I have two choices, either to pick A or to leave it. Similarly, if I chose not to pick C, I again have two choices, either to pick A or not to pick B. Sorry, not either to pick B or not to pick B. Then we have two choices here also, to pick A or leave it. Similarly, here also we will have the two choices, to pick A or not to pick A. Now if you see, if we are following this path, when we are picking C, then we are picking B, and then we are picking A, we are basically picking all the elements, that is A, B and C. But so we are picking A, B, C here. If we follow another route, that is we are picking C, we are picking B, but we are not picking A, then in this case we are picking elements B and C, right? Similarly, we can see for this case, we are picking C, we are not picking B, but we are picking A, so we are picking A and C. And in this case, we are only picking C. In this case, we are picking A and B. In this case, we are picking element B, and in this case, we are picking only A, and in this case, we are picking nothing. So this is the recursive tree for the recursive approach we are making, either to pick or to not pick. This shows pick and this shows not pick, and the same can be said for the recursive subtrees possible here. Now let's just see the time complexity and space complexity for this brute force approach or this recursive approach. As we can see, we are having n elements, right? And for every element, we are having two choices, that is to pick and not pick. So can I say that I am having two choices for n elements? That means in this case, as you can see, how many choices we were having? 2 into 2 into 2. So a total of 8 permutations are formed for this example, as you can see. It is 1, 2, 3, 4, 5, 6, 7, 8. So in this case, the total permutations form were 2 raised to power 3, where 3 is number of elements. So can I say the time complexity is big O of 2 raised to power n? Yes, so the time complexity is big O of 2 raised to power n. Now let's discuss the space complexity here. In this approach, we are not using any extra space, but still, since we are using recursion, we are using the call stack space. And how much is the call stack space? If we observe carefully, then for any recursive call, the max space which we are using is C, like this, here 1, 2 and 3. Then if this call gets over, then it moves to this call. So in the worst case, for every possible case here, we are using only the space 3, which is the size of the items array. So we can say that the space complexity is big O of n, that is the call stack space. Now that we have discussed the time complexity and space complexity for this approach, let's see what will be the solution for this example which we were discussing. So let's see for all these permutations, we will just see what will be the total value evaluated and what will be the total weight, and then we will pick the permutation giving us the maximum value and the weight less than the knapsack capacity. So I have already computed the value and the weight for all the 8 permutations. The 8 permutations are as follows, which we have already discussed before, and the value for when we are choosing nothing will obviously be 0, and the weight will also be 0. And since this weight is less than our knapsack capacity, which is 12, we can consider this. Similarly, we can consider the second permutation because its value will be 20 and weight is 2. And similarly, we can see for all these permutations, the maximum value which we will get and the weight of those items should be less than equal to the knapsack capacity. Then the maximum value which we can get will be 85. And hence 85 will be our answer. Alright, now let us just code our recursive approach. So for code, we will just code it, but before moving on to the code part, let us just discuss the pseudocode first and the general idea which we will be following. So the general idea which we are going to use is that we are given this array of items consisting of values and weights and a knapsack W. Now what we are gonna do, we are just gonna check, let's say this is n items, then let's say we start from the last item. You can even start from the first item, but I'm starting from the last item in this case. So this item would be n-1th item. Now I will make a choice here, either to pick this or to not pick this. Also, I need to make sure if I'm picking it, then the weight of this n-1th item should be less than or equal to the weight of my knapsack. And for not picking this, there is no condition that I need to follow. Now after making the choice, either I'm picking it or I'm not picking it, I will move on to the remaining part of the problem. Then since I have solved for this one, I will be solving the remaining portion of this array, that is for n-1 elements, and this will be solved by recursion. Now since we are using recursion, so recursion consists of basically a base case and then the remaining induction part. When we made a choice of picking and not picking and calling the recursion again for n-1 elements, we are done with the induction part. Now let us discuss the base case. So the base case would be when no elements are left, right? So when no elements are left, and if we see that the weight of knapsack, or not the weight actually, the sum which we are getting, we will have a variable sum to store the values of the items which we have picked. We will pick the maximum value of sum when no elements are left. Now this is just a general idea and some sort of pseudocode you can consider. Now let us just code this brute force approach or the recursive approach completely. So let's say this is our function that is going to return the maximum value possible for given n items and weight W of the knapsack, and we are given two arrays, the WT array and the val array, for denoting the values and the weights of the given n items. Now to solve this problem, since we know we are using the recursive method, so let's first consider the base case. And the base case would be if there are no elements left, that is if n is 0. Now here we also need a variable, let's call this answer, that will be our final answer for given n elements, the maximum value which we can obtain. Now in the base case, if n is 0, that means we cannot pick any element. So when we cannot pick any element, we will simply return 0. That will be the maximum value which we can get when there are no elements. Otherwise, we need to do the induction. By induction I mean we can either make a choice to pick the element or not pick that element. The element would be the last element in this case, so that would be n-1th index. So when we are picking, as I have already told you, that we also need to check a condition for picking, that the weight of this n-1th element should be less than or equals to the knapsack capacity. If this is the case, only then we can pick the element. So for picking this element, we can just say that the answer would be taking the value of this element plus solving for the rest of the cases, that is for n-1 elements. So I can just write knapsack for the remaining n-1 elements. Now since we have picked this element, we need to subtract the weight of this n-1th element from the knapsack capacity for the remaining n-1 elements, and we will be passing the weight array as it is, the value array as it is, and the remaining items will be n-1. This is the case when we are picking the element. But as we know, if we can pick, then that doesn't mean that it will always give us the maximum value. So we need to also consider the not pick condition if we are considering the pick option. So here we will take the maximum of pick and not pick. So I will just use max function here, and this is for pick, and if we are not picking the element, we will just call the same function for same knapsack capacity, the weight array as it is, the value array as it is, and n-1. So this was the case when we can pick the element. Then we will make a choice to pick or not pick the maximum value which we will get among the two. But there could be a case when we cannot pick the element. In that case, we will not make any choice. We will simply say that answer would be the knapsack for the given weight capacity, the weight array, the value array, and remaining n-1 elements. That is, we are not picking it. And then we can simply return the answer. Now let us just copy this code and try to submit this in an online ID so that we can verify that our code is correct. So let's try submitting our code on the Geeks for Geeks platform. And we should be getting a time limit exceeded error because we have not optimized it using dynamic programming, and that is exactly what we got. So we are getting a time limit exceeded error, but we are passing all the test cases. That means our code is correct, but we need to optimize it using dynamic programming. Now before moving on to the optimization using dynamic programming, I would like to discuss how the greedy algorithm fails on the 0-1 knapsack problem, because sometimes it might come to your mind that if we just need the maximal value from the given items, why not we just take the items which are most valuable. By most valuable I mean which are having less weight but more value, and that means following the greedy approach. So let us just discuss that. So let us just consider the same example which we solved right now. So using the recursive approach, we were getting the max value possible from this knapsack problem to be 85. Now let us just apply the greedy approach, and for greedy approach we need to know, we will first pick the most valuable item. So let's decide the most valuable item. We can decide that by taking the value by weight ratio, that is those items which are having more value but less weight. So if the value by weight ratio is high, that means that item is more valuable than other items. So the value by weight ratio for these items A, B and C would be like this. In this case, here it would be 10, here it would be 6.25, and in this case it would be about 7 point something. So we can see the most valuable item is item A, then is item C, and then is item B. So if we want to apply the greedy approach, we will first pick the most valuable item if its weight is less than the knapsack capacity. So we will first pick item A, and its weight is 2 and the knapsack capacity is 12. So we will obviously pick this most valuable item. So once we have picked it, our knapsack capacity will be 10 and the value which we have obtained so far will be 20 on picking item A. Now after picking item A, the items left are C and B. Out of these, the most valuable is item C. So we will just check the weight of item C, and that is 8, and our knapsack capacity is 10. So we will again pick item C. Now the knapsack capacity left would be 2 because its weight is 8 and A's weight was 2, and the value which we have got would be adding the value of C which is 60. So 20 plus 60 will become 80. Now we will, after picking the element C, now the only element left and the most valuable element now would be element B. So can we pick element B now? Its weight is 4 and our knapsack capacity is 2. So we cannot pick element B, and using greedy approach, the answer we are getting is 80, which is not correct, because using recursive approach, we have already seen on picking items B and C, we can get a value of 85. But using greedy approach, we are getting answer as 80. So hence this proves that greedy approach fails on the 0-1 knapsack problem, and that's why we should try to solve this problem using dynamic programming. Now let us just discuss the further optimization of the previously discussed recursive approach using dynamic programming. So what exactly is dynamic programming? We have earlier solved the recursive, we have already solved the 0-1 knapsack problem using the recursive method. Now to optimize this, we are going to use dynamic programming. But basically, what is dynamic programming? This is nothing but recursion plus storage. When we are doing a recursive call, let's say recursion call starts like this, then it moves to another call. Let's say this is a recursive tree. But this call, let us say this call is exactly same as this call. And when we are doing recursion, when we are solving this call, we are when we are moving back and again making a call here, we are wasting our time to solve this problem again. So dynamic programming, what it does, it uses a storage. It may be in form of array or vector, maybe a matrix, or maybe some hash map, to store already computed answer, so that we do not need to compute it again. So what we will do in dynamic programming, once we solve the answer for this subproblem here, and when we reach here in this recursive tree, we will directly take from the answer from our storage, and we will not be solving this again. So the time to solve all this problem will be saved, and hence it enhances our time complexity. Now let us discuss the method to apply this dynamic programming in our recursive approach, which we discussed earlier. Let's use the memorization approach in our recursive approach so that we are able to use the dynamic programming and optimize our approach. So how will we do that? Let's see. First of all, we need a storage. So let's say we are having a 2D matrix in this case, and in this case let's say we are passing it in our function here. So we are going to just pass our storage also here. Let's say that this is our 2D matrix, so let's say this is a vector integer, and we need to pass this by reference. Let's call this a dp. There's no problem if it is not clear right now. It will be clear when we will code along. So we just need to pass a 2D storage. This is basically a 2D storage or any kind of storage which you like to use for implementing this memorization in a recursive code. So once we have passed this code, we just need to check for converting our recursion code to memorization, that is to use memorization technique and implement dynamic programming in our code. We just need to follow the following steps. The first step is to create a storage which we have already run and pass it to our function, and recursive function to be to the point. The second thing is, in the starting of this function, we just need to check if answer for given sub problem already exists. If the answer already exists in our storage, we can simply return the function call without computing it because we have already stored the answer in our storage. If it is not present in our storage, what we will do? We will just compute the answer and store it in storage for future use, and that's it. If we will follow these 3 steps, then we will convert a recursive code into a memorization approach. The first is that we need to pass this created storage in a recursive function. Like here I have passed the 2D matrix, a dp, I'm naming it dp. Now we just need to initially check here in the starting of the function if we are having the answer for this particular values for given weight, for given knapsack capacity and given number of items. So in this recursive function, we will initially just check our storage if it already contains the answer. How we are going to check that? That if our dp for n items and given w knapsack capacity is not equals to -1. Let's say we have initialized this by -1. So if it is not -1, then we have already computed for this sub problem for given n and w, and in that case we will simply return this already computed answer, that is dp and w. And when we are returning this answer, we will not return this answer simply. We will store this in our storage also, that is dp and w equals to the answer, so that in future if we have to compute this problem again, we will not compute it again, we will directly pick the answer from this storage. And using this we have implemented the memorization approach and we have optimized our code. Also, let's discuss how to decide the size of our storage. In this case we need a DP storage of say size n plus 1 and the initial knapsack capacity plus 1. How do I come to this conclusion? Because for any subproblem, what we can see when we are calling our recursive function, the parameters which are changing are the number of items, the weight of knapsack, and the rest of the parameters like value, weight, they remain same. So only these two are the changing parameters. So we need to find out the changing parameters for each subproblem. And you can observe that when we are calling a smaller subproblem, then only n and w are the parameters which get changed. So we will make a storage for changing these, for storing all the values when these are changing. So in this case, we have chosen to make a 2D matrix so that we will have something like this. This will be for all the, by n plus 1 we will have all the values till n minus 1, and for w plus 1 we will have all the values till w minus w, and in this case it will be n, so that we can store all the subproblems whatever may be the n and w value. N may lie between 0 to n and w till 0 to w. Now in this table we can store all these subproblems easily. That's why we have taken the bounds of this 2D matrix as n plus 1 and w plus 1. So let's revise what we have done once again. In our recursive approach, we were always computing the problem again and again, even if we have solved that problem before. For example, if this was the tree, and let's say this is the recursive tree we are having, and this problem is exactly same as this problem. So when we solve this problem here, we have already solved for this much part, and in this recursive approach, when we were again coming to this part, we were solving this again. But using dynamic programming, when we solved this first time here, we stored this answer in this DP table somewhere. Let's say this is for a particular n and w, and this is that n and w. So when we will come here, it will not again compute the answer for this subproblem. It will directly take the answer from here and save our time. So this is how we have used dynamic programming using this storage and optimized our answer. Now let's implement this memorization approach in our code. So now let's implement the memorization approach in our already written recursive code. So the first step which we had to follow was to create a storage. So in this case, let me just create a storage. I'm gonna use a 2D matrix. Let's say I'm creating a vector int. Let me just call it TP, and the size, as we have discussed, will be n plus 1 and w plus 1. So this is the size, and also I would like to initialize the complete matrix by -1. Here -1 denotes that this subproblem has not been solved yet. So once we have created the storage, we also need to pass this to our recursive function, and let's pass this by reference so that we can update it within our recursive call. So here I will just use this knapsack function with given weight w, with the weight array, with the value, with the number of items, that is n, and also I would be passing this storage, which is TP. And here also in this function definition, I would like to make some changes by accepting this storage. This is vector int, and I will pass this by reference and %dp, and I would like to make the same changes here also. So I will just mark it as dp here, dp here, and dp here. So this was the first step to pass to create and pass this into a recursive function. So now what is the second step? Second step is to check before making any computations if we have already solved this problem before by checking if the solution exists in the storage for given n and w. So let's just consider this as a base case. So another one more base case we need to add, which is if dp for given n and w is not equals to -1, that means we have already pre-computed the answer for given n and w, and that means we can simply return this sub problem and we do not need to compute it again. So we can just return dp n comma w. And another base case which is same as before, that if n is 0, we simply return 0. But here some modification which we will do, that dp n comma w, because we also need to save this in the storage. So let's save this in the storage, that return dp and w equals to 0. Now we just need to implement the last step, which is to save the answer in our storage when we are returning it. Just dp and w, that we are gonna return dp and w equals to answer, that is we are returning the answer and at the same time we are storing this answer in our storage, so that when we make same call in the future, we can directly take this answer from our dp storage. Alright, so now let us just copy this code and run this in our online platforms and submit it and verify the solution. Now here, since we cannot have access to main function, so we need to create our storage from here only. So we will just create a storage. Let's call this dp of size n plus 1 and w plus 1 and initialize it with -1. This is the create storage step. The second step is to pass this in the recursive function. Now since this is not our recursive function, we will make a new function which we will call KnapSack, and we'll copy paste our already coded recursive function in this new KnapSack function with smaller s. So here what we are gonna pass, we are just gonna pass w, weight, value, n, and this newly created storage dp, and we are gonna simply return this as our answer. Now let's create this function, which is when we copy paste our this function, which is this. So we have copy pasted this code here. Now we need to make some changes, like we need to fix this. We need to make this as small here and this as small here, and the same thing here and the same thing here. So let's once again see what we have already done here. That in the base cases, one of the base case was to check existing solution in storage, and when we are returning the answer, what we were doing, we were storing answer in storage as well when we are returning it. And so that's it. Now let's just try to run this. So you can see just by these 3 lines we have converted the recursive approach into a memorization approach. Now let's submit this code. Now you can see we have solved this problem successfully because we have already used the dynamic programming. Although we have already used dynamic programming and the solution has been accepted, we will still make some further optimization using the tabulation method and some further space optimization. So let's do that. Now what is tabulation method in dynamic programming? Previously we just discussed the memorization method. Although that solution got accepted, but even more optimized version is the tabulation method. Now let's discuss why. So what we were doing in the memorization approach, we were simply using recursion plus storage, right? So it was recursion plus storage. Now how does recursion work? We start from a bigger problem and break it down into smaller problems, and by solving these smaller problems we derive the solution for this bigger problem. So this is like a top-down approach. So for getting the solution to this bigger problem, first we need to go to this smaller problem, then this smaller problem, and we need to go till the base case of the recursion. That's why it is called top-down approach. So as you can see here, we need to use some call stack memory because we are using recursion. So, and that is big of n if there are n items. So for getting the solution of this bigger problem, first we go till the base case, then after getting the solution we again go back to the bigger problem. Wouldn't it be better if we start from this base case only, we get the solution for this, then we move on to get the solution for this, and then this? If we do from bottom up approach, that is starting from base case only, then we will not use the call stack space, or we can say we have avoided recursion, because then we can solve the problem using iterative method. Let's see how. In bottom approach, first we'll get the answer for base case, then we will move on to solve this problem. So we will get the answer of this problem using already solved base case. So we will store the answer here, then we will use this answer to get the answer for the final problem which we need to solve. And what was happening in top-down approach? For solving this problem, first we keep this in our stack, this bigger problem, then we move to this problem, then we store this problem in our call stack, and then we get this problem, then we store this problem in our stack. Now getting the base case solved, we pop this, then we get solution for this, then we pop this, and then we get solution for this. So we were using this call stack. Now when we are using this bottom up approach, we have completely avoided the use of call stack memory. So that's why this bottom up approach, or you can say the tabulation method, is better than our memorization method. Now let's see how to implement this tabulation method. So I have just taken our previously implemented memorization code. So this is the memorization code. Now let's convert this into tabulation approach, tabulation method. So in this, what we do, we will start from the base case only. Like in this case, let's say this is our DP table, and this is the W, and this is the N. So we were filling it starting from the bigger problem, and let's say the bigger problem is this for N and W. Then we will break it into smaller problems somewhere here and here. These will again go and ask for some smaller problem till here, and then we will finally, these will move on till this some base case. This will be the base case somewhere here, which is you can see if n is 0. So if n is 0, then these are all the base cases where the answer is already 0. And from using these base cases, we derive the solution for this and this. Using these two, we derive solution for these bigger sub problems, and finally we get the answer for our main problem in the memorization method. So what we do in tabulation method, we again have the same matrix, but here, since we already know the answer for base case, and this is W, we will already say that the answer for the base case is 0, right? And now we start filling this table from these cell values. We will fill this value using already filled values, then we will fill this value using already filled values, and finally we will reach till this point where we have filled all the values using already pre-filled values before. And this way we will iteratively solve this recursive problem and we will save the call stack memory. Now for example, just see, when n is 0, we know that the answer will be 0. Also, when the knapsack capacity is 0, it doesn't matter whatever items are left. If the knapsack capacity is 0, we cannot pick any of the items. So in this case also, all these values will become 0. So these are all our base cases which we have filled in this matrix. Now we will start filling from here. Now just see, for this case, let's say this is w equals to 1 and n equals to 1. So for this element, if we see from our memorization code, what are we doing? We are having two choices. Either we are picking this element or not picking this element. So we will implement the same thing here also, but this time let's say this is our, when we are iterating over these n values, this is our I and the w is our j. So this becomes I comma jth cell. So what we can do, we can simply say that if the weight of the I minus 1th item is less than equals to the knapsack capacity, we can simply convert this code from memorization to tabulation, that the answer would be then maximum of I minus 1th index plus knapsack of and not actually plus knapsack of, let me just write it over here. So basically, let's just do it once again. In tabulation method, what we are doing, when we are initializing our matrix, so let's say the DP table, we have initialized it with the zeros for the base cases, because we know for the base case answer is 0. Now we will start iterating from this value, like this, then this and this. So we can start from I equals to 1, I less than equal to n, and I plus plus. And then we will iterate from j equals to 1, j less than equal to w, and j plus plus. And now we will implement the tabulation method in this thing, because now what is this loop doing? We are iterating over all these values like this. Now how to find the value for this particular cell? Now we can observe one thing. We can either pick the element. If we can pick the element, then as we already discussed, if we need to pick the element, then the condition is that the weight of that element should be less than the knapsack capacity. And here we can see the j denotes the knapsack capacity. So can I say that if the weight of the element is I, so if the weight of my ith element, because when there were n items, we were taking n minus 1th element. So in this case, can we say if there are I items, then the I minus 1th element is the one which we are talking about. So the weight of I minus 1th element, if it is less than equal to the weight of the knapsack. And what is the weight of the knapsack? In this case, we can see that weight is denoted by j. So if that is less than equal to j, then we have to make choice to either pick or not pick and take the maximum value. So we can say that the value for dp ij will be the max of pick and not pick. Right now I'm just writing the pseudocode. It will be much more clear when we code it in the code editor, and otherwise we know that dp ij will be not pick. Now what will be these pick and not pick? So if we are discussing about this pick, then we know that if we are picking, then we need to calculate for n minus 1 items and w minus the weight of the current element in the memorization approach. Now let's convert this into tabulation method. So in tabulation it would be converted like we need to if we are picking this element, then this will be the value of I minus 1th element plus the solution for n minus 1th element with weight reduced from the current element. So, and we already know the solution for the I minus 1th element, and the weight is j minus weight of I minus 1. So this will be the condition for pick, and for not pick this will be dp I minus 1 and j. So let's see one more time what has changed in memorization and tabulation. What we were doing in memorization. In memorization, we were starting from this n comma w. For this we were calling subproblems. These subproblems again called another subproblems and reaching the base case. Now these base case solution we knew, so we will get the answer for this. This will give answer for this, and this will give answer for the main problem. But in tabulation method, what we are doing, we are starting from bottom up manner. We know the answer for base cases, so we are directly generating answer for all these problems from already known solutions. So the call stack memory is saved. When I'm getting answer for this one, I know I will be using the values from here. These values are the ones I'm gonna use. For example, if I'm computing the solution for this subproblem, then I will use only the subproblems answers which are already known to me. Like you can see that if I'm solving for dp I comma jth value, for pick I'm picking value I minus 1, and the dp I'm using is for dp I minus 1. If this is I, this will be I minus 1, and j will be j minus somewhere between these values. So these are already pre-computed, so I'm sure that I have already computed the previous answers, so I can compute this value using my previously calculated answers. Similarly, I can do the same process for all of these values, and finally I will reach this value, and this will be my final answer, which is dp and w. It will get more clear when we code it in our main code. So now let's do that. So this was our memorization code. Now the first step is same, that we need to create a storage, but now instead of passing this to a recursive function, we will do this iteratively. So we do not use any call stack space, so we will remove this line, and we also do not need this function. But to write the iterative code, we need help from the memorization thought process. Since we know that in the base case, whenever n is 0, our answer is 0. So let's say I'm initializing my matrix by 0. So that I'm initially saying that all the values are 0. Now I will update those values which will get changed. Now since I know in the base case, whenever n is 0, that is there are no items, then the knapsack capacity, the maximum knapsack capacity I can have will be 0. And also whenever the weight, the knapsack capacity is 0, then doesn't matter how many elements I have, my answer would be 0. So if n is 0 or w is 0, then in that case my answer will always be 0. So I will start filling my table from I equals to 1 till I less than equal to n, and my weight will be iterated from j equals to 1 till the knapsack capacity. Now here what we need to do, We just need to follow this induction process. The only change is that we are sure we have already computed the previous subproblems and not starting from bigger to smaller. We have already computed the smaller problem and now we are computing the bigger problem. So for this dpi, j problem, I am assuming if I'm not picking this first. So if I'm not picking this, then what will be my answer? If I do not pick this, then my weight will remain same, that is j only, because j denotes the weight, and I need to solve for the remaining n minus 1 elements. That means I minus 1 elements. But if I have the option to pick, then that means my dp I comma j will need to choose from maximum of pick and not pick if I am allowed to pick. So now let's replace this pick and not pick. So if I will pick the element, then the value will be value of I minus 1th element plus the solution for I minus 1, and the weight would have been j minus weight of I minus 1. Right? Let me explain this once again. If we can pick this element, and yeah, if we can pick this element, we need to have this condition that the weight of, if we are picking ith element, then the weight of this I minus 1th element should be less than equals to j, because j denotes the weight of the knapsack, or I should say the knapsack capacity. Then in that case, the solution for I elements and j knapsack capacity will be the maximum of picking this ith element, which will be taking the value of I minus 1th element in the array, plus the solution for I minus 1 elements with weight reduced from this I minus 1th element, that will be j minus weight of I minus 1. So this is pick, and we need to take the maximum value of pick and not pick. So the not pick, I have already marked dpij as not pick, which is, so I can directly state dpij here, that means not pick. So once we are done with this, all after end of this complete loop, our complete dp table will be filled, and the answer which we need will be stored in dp n comma w. So we can simply return, or not return, just print this, because this is the main function. We will just print this dp n comma w, which will be our answer. So this is using tabulation method. So now let us just copy this code and verify this solution on the online platform. So let's remove this memorization approach which we did earlier and use our new tabulation approach here. So first what we have done, once again, we have created a storage. Then we are filling our dp table, and the base case we have already initialized with 0 in the table. Now we are filling the remaining values, filling the dp table, and so we have two choices. Either we will not pick, and if we can pick, we will pick the maximum out of the pick and not pick choices. And finally, when we will have all the dp table filled, the main problem was n elements and w knapsack capacity. So we can return simply dp n and w, and that is a tabulation version of our dynamic programming for 0-1 knapsack problem. So let us just submit this code. And we have solved the problem successfully using the tabulation approach. Let us now discuss further space optimization in 0-1 knapsack problem. And before that, let us also revise the time and space complexities which we used in all the methods till now. The first was the recursive method. In that, the time complexity which we were using was big O of 2 raised to power n, and the space complexity was only big O of n because of the call stack memory which we were using because of recursion. So this was because of call stack memory. Then we learned about the memorization method when we optimized the redundant overlapping problems and reduced our time complexity to big O of n square. Why big O of n square? Because we know that we were creating a table of n cross w size, so you can consider it as big O of n into w also, but that can be easily said as big O of n square. If you consider the max of n and w, then you can say this reduces to big O of n square. So if every cell can be only filled once, if any problem is, let's say we have already computed this problem and we are in the recursive calls, we again want to compute this problem, then we are directly taking this value from this storage. So in the worst case, all these cells will be filled, and thus the time complexity becomes big O of n square. And the space complexity becomes big O of n square for this space used for this storage plus the call stack memory, because we are also using recursion, so that is actually big O of n square only. But we cannot ignore the fact that we are still using a call stack. And finally we discussed the tabulation method. In the tabulation method, the time complexity is same as big O of n square because of the same concept. We are using the DP table, but the space complexity is only big O of n square because of this table, but the call stack memory is removed here because we are not using recursion. This is iterative. So far this was the these were the methods. Now in this tabulation method, we can further reduce the space to big O of n. Now how we are going to do that? Let's see. So what are we doing so far in tabulation method? We are basically we know in the base case, we knew that all these were 0 because they are base cases. Whenever the n is 0 or w is 0, so they were all 0. And now we were just filling the table from starting from here till here, then here, and in the end we just needed this cell as our answer. But now just observe one thing. When we are filling any cell, say dp I comma j, there are only two choices. One is pick and one is not pick. So when we are not picking, we know that dp ij was dp I minus 1 comma j, that is reduce the element by 1 and keep the knapsack capacity as j only. So let's say if I'm filling, this is my I and this is my j for the current iteration, then for this value if I'm not picking, then dp I minus 1 j is nothing but this cell, and if I'm picking the value, then my dp ij is value of I minus, if there are I items, then the value of I minus 1th item plus dp of I minus 1 comma j minus weight of my I minus 1th item. And this can only be applied if this j minus weight of I minus 1 is greater or equal to 0. So what will be this? This will be anywhere between these, right? dp of I minus 1, because if this is I, I'm sure this will be I minus 1, and j minus weight of I minus 1 can, if this is j, then this can lie between here to here. So what can we observe from this? if I want to fill the value for this cell, then I need pick or not pick. So if I'm not picking, I will need this cell, and if I'm picking, then I will need any cell from these cells, these 4 cells. So in worst case, if you see, let's say I want to fill this cell, then I can fill this cell easily by this array, because this will be not pick, and any of them will any of these one cell will be pick, will give me the value for pick. So for filling this row, I only need this row, so I can discard the above table, right? So by this I mean, instead of using a table, we can use a 1D array, and that will reduce our space complexity from big of n square to big of n. Now let's see how. So in tabulation method, exactly what we were doing, we have already initialized the values for the base case as 0. Now for the remaining values which we were filling the table, when we were filling the table, we were doing it like this: for I less than equal to n and I plus plus, for j equals to 1, j less than equal to w, and j plus plus, and then we were making pick, not pick choices, and after the complete table is filled, we were simply returning the value for dp n comma w. So now instead of this 2D table for optimization, what we will do, we will only create a 1D table. Let's say the 1D table is dp with size w plus 1 and initialize all of them as 0. Let's say this is our 1D dp table, which is initialized as 0. Great. Now for every iteration of this I will make a temporary table. Let's say because for the next iteration, what we have observed, for filling this row we needed this row. So let's say this is our dp table. I will make this new temporary table here and fill this using this dp table, and then replace all the values of this dp with this temp, and again iterate for next time and again fill this temporary table and fill the values of temporary table using dp table till n iterations. It will be more clear when we will discuss this serial code and the complete code. So I will create a temporary table here. Let's say this is the temporary table, and let's say this is equals to my dp table, because I want to copy the same table in this temporary table initially. Now if I do not want to pick, since I have already copied these values, which is 0 0 0 0 0 0 in this temporary table, and if I do not want to pick, I in the dp table what we were doing, if we do not pick, we just pick the top value, right? So since we have already copied the top value, we can completely remove this not pick condition because it is already not picked. Now if we are gonna pick, then we need to check this condition: if the weight of weight of I minus 1th element is less than equal to j, if this condition satisfies, then we will update our dp, the temporary array. Let me just do it a little more clearly. So we will just update our temporary arrays. Let's say we can pick an element here, so I will just update this temporary jth position, because this is jth position and this is temporary array, with the maximum of its current value, which is not pick, so that is temporary j position, and so this is not pick and the other value will be pick, and for pick that would be value of I minus 1 plus the dp table for j minus weight of I minus 1, which will be somewhere between these values. Let's say if this is this one, we will take max of these two values. If this value is this, we will take max of these two values. So this will become the pick condition. And once we are done with this J loop, we will do one last thing. We will update this dp table as the temporary table. So we will copy all these values of temporary into our dp, and in the next iteration again create a new temporary table and do this for n iterations, so that in the end we will have dp table and this column will store our answer, because in the last iteration this will give us for the nth element and this will give us for w knapsack capacity. That means for n items and w knapsack capacity, that is what we want. So we have by following this, we have reduced the space complexity from big of n square to big of n for tabulation method. Now let's implement this in our code. So let us just first create a 1D dp table of size w plus 1 and initialize it with 0, because we know for the base case when n is 0, the answer is 0. Now once we are done with this, we will start with our tabulation method for I equals to 1 till I less than equal to n and I plus plus. Now here we need a temporary table. Let's call this temporary table, which will be equal to our dp table. Now we will start the iteration for the knapsack capacity, that is j equals to 1 till j less than equal to w j plus plus, and we will update the current j's value only if we can pick the element, because we have already copied all the values from the dp table, so the not pick values have been copied in this temporary table. So if we can pick, and if we will be able to pick only weight of this, if there are I elements, then the weight of I minus 1th element should be less than equal to j, and in that case we can simply pick the element. So we will update the temporary table j value as max of its current value. Current value will denote the not pick, and this value of I minus 1 plus dp of j minus weight of I minus 1 will denote the pick value. And once we end with this j loop, we need to copy all the value of temporary array into our dp table. So for int j equals to 1, j less than equal to w and j plus plus, we can simply say that dpj will be equals to temporary j, and in the next iteration we will get the values for the remaining. We will keep on iterating till n, so that we get the value for n items and w knapsack capacity, and finally we can return dp of w, because it will store the maximum value which we can obtain for n items and w knapsack capacity. So now let's just try to submit this code. So we have solved this problem successfully with further space optimization. With this, we have covered all the concepts of the 0-1 knapsack problem. Thank you.